Good afternoon, and welcome to this session. We hope you are having a great time at the summit so far. My name is Roy Alela, and I'm a senior AI/ML specialist solution architect at AWS. And today I'm joined by...
Hi everyone, I'm Jingya. I'm a machine learning engineer from Hugging Face. I maintain and develop the Optimum Neuron library that we will talk about very shortly.
Large language models offer a wide array of possibilities, yet adapting them for our use cases and deploying them can be a challenge. Today, we'll walk you through how to efficiently fine-tune and deploy these models on our purpose-built machine learning accelerators, the AWS Trainium and Inferentia tool, using the Optimum Neuron library from Hugging Face. We have a packed agenda, so let's dive in. We'll first look at the business need for fine-tuning these models, and this will help set the context for why this is a critical topic in today's AI landscape. We'll then explore our purpose-built machine learning accelerators, the AWS Trainium and Inferentia, that enable you to optimize your AI workloads for cost efficiency and performance in the cloud. We'll introduce the Optimum Neuron library from Hugging Face that enables developers to fine-tune and deploy their models on these accelerators, leveraging the familiar Hugging Face API. We'll cover the fine-tuning workflow on AWS Trainium and how to deploy these models into production using Inferentia 2. So let's get started. Let's take a moment to understand the evolution of large language model customization techniques. This curve illustrates an increase in cost and complexity as we move towards more advanced techniques. At the bottom left, we have prompt engineering, and this is where we craft specific prompts to steer the model's output. While it's simple and straightforward to implement, it offers the least room for accuracy improvement. Moving up, we have retrieval augmented generation, and this is where we aim to enhance the model's accuracy by providing it with relevant external information during the generation process. While it performs better than prompt engineering, it also results in an increase in cost and complexity because we have to implement and maintain a knowledge base. Next, we have fine-tuning. And fine-tuning involves adjusting the model parameters using domain-specific data set for our use case. While it might result in an increase in cost and complexity, a recent work in the rise of smaller models and techniques such as parameter-efficient fine-tuning have reduced the associated costs and streamlined this workflow to reduce the complexity. And right at the top, we have pre-training, where we take a base model and train it on a large text corpora in an unsupervised manner. And pre-training offers the highest potential for accuracy improvement. However, it's the most costly and complex method to implement. As we move up the curve, we see a clear trade-off. Higher accuracy comes at the increased cost of complexity and resource requirements. Thus, it's essential to evaluate these techniques based on your use case, domain expertise, budget constraints, and the size and quality of your dataset. In today's session, we'll focus solely on fine-tuning as it offers a fair balance between the accuracy improvement and the practical implementation for most businesses. So let's see why smaller models have made fine-tuning more compelling. So why has there been a notable increase in the adoption of smaller models like Llama 3.8b and the Mistral 7b for fine-tuning? What benefits do they offer? Besides requiring less compute resources and power to train, fine-tune, and deploy, these models also result in improved performance. Recent research and benchmarks show that smaller models, when fine-tuned on high-quality dataset, can result in considerably high accuracy. These models also have smaller sizes, and thus this results in a reduced memory footprint. And because these AI workloads are memory-bound, the reduced footprint enables faster training iterations and reduced inference, which is desirable for real-time applications. The smaller models are also easier to deploy, update, and maintain in production. The simplicity in management reduces the operational overhead and potential points of failure. As a business, when you fine-tune the models, You get greater control over the model's capabilities and outputs, enabling you to align the model to your custom needs. It also enables you to build your unique IP in order to differentiate your market offerings. The smaller models also offer flexible deployment options, such as efficient scaling and auto-scaling, to enable you to optimize for cost and performance based on your usage demand. They also enable you to deploy on edge applications and mobile devices with limited resources. And finally, open source AI communities, most notably Hugging Face, have done a commendable job in democratizing access to models, datasets, and tooling to streamline the fine-tuning workflow. This community-driven approach has accelerated AI innovation and made these advanced techniques accessible to a wider audience. Let's explore our purpose-built machine learning accelerators that enable you to optimize your AI workloads for cost efficiency and performance in the cloud. First, we have the AWS Inferentia 1. This is our first-generation inference accelerator launched in 2019. It offers the lowest cost per inference for your deep learning models, and you can achieve up to 70% cost savings versus comparable EC2 instances for your deep learning models. We also have our AWS Inferentia 2, which is our second-generation inference accelerator that is purpose-built for your large language models and diffusion models. They offer up to 4x higher throughput and 10x lower latency compared to the previous Inferentia 1, and you can achieve up to 40% cost savings versus comparable EC2 instances. To enable you to fine-tune and train your large language models and diffusion models, we offer the AWS Trainium, which is our training accelerator. And this is the most cost-efficient and high-performance training accelerator that can enable you to achieve up to 50% cost savings versus comparable EC2 instances. These cost and performance benefits make these accelerators very attractive for deploying your AI workloads. And let's look at some customer success stories that affirm this. There is a rapid adoption in the growth of these accelerators across various industries and use cases. And to highlight some customer success stories, we have Stability AI, who are able to reduce the cost of the stable diffusion XL model by up to 60% per image and realize a 30% cost saving when training on Trainium. By leveraging Inferentia 2 for their sales and service AI agents, Deutsche Telekom were able to realize a 25% improvement in model responsiveness, resulting in faster resolution times. And Ninja Tech, who are building AI agents based on the Llama 370B models, were able to realize up to 80% cost savings versus comparable GPU instances. Other notable industry leaders leveraging these accelerators include Anthropic, Adobe, Databricks, Snapchat, and the list goes on. We are also leveraging these accelerators at Amazon and across several Amazon services such as Amazon Alexa, Amazon Advertising, Prime Video, Amazon Robotics, and Amazon Recognition. Let's take a moment to understand and see the key features and benefits that make the AWS Trainium the ideal platform for fine-tuning and training your AI models. You can expect up to 50% cost savings versus comparable EC2 instances. And with up to 1,600 gigabits of network bandwidth, these instances offer rapid data transfer and communication, which is critical for your distributed training scenarios. The network is based on the second-generation Elastic Fabric data, which enables reduced congestion, lower latency, and cluster-level scaling. Each Inferentia chip comes equipped with 32 gigabytes of accelerator-like memory, scaling up to 512 gigabytes on the larger instances to enable you to load your larger models with larger batch sizes and longer context lengths, which is becoming a key industry requirement. We offer these instances in 3 configurations: the entry-level TRN.2x large with 1 Trainium chip for your smaller models, and the enhanced TRN1.32x large with 16 Trainium chips and up to 800 gigabits of network bandwidth for distributed training. And we have the enhanced networking variant, the TRN1.32x large with up to 1600 gigabits of network bandwidth for more efficient distributed training. The various instance options enable you to scale out your compute resources to meet the specific demands of your training and fine-tuning workloads. So let's put this into perspective. Let's assume you have a company use case where you want to build a chatbot based on your company data, and you have evaluated various techniques and settled on fine-tuning the Llama 2 models to build your company chatbot. So what performance numbers can you expect? On the Trainium, you can expect up to 46% cost savings versus comparable EC2 instances. And if we are to look at the effective teraflops per dollar, which is a measure of the cost efficiency, the higher the number, the better the performance per dollar spent. And for the Llama 2 7B, we are able to achieve up to 155 teraflops per dollar, which is 1.86 higher than the comparable EC2 instances. If you opt to fine-tune the Llama 2 70B on larger data, you can expect up to 125 teraflops per dollar, which is also 1.86 higher than the comparable EC2 instances. The consistent 1.86 scaling is important as it showcases that the efficiency gains scales well with the model sizes, thus adhering to the scaling laws in model training. Now, let's shift gears to look at the key features and benefits that make the AWS Inferentia 2 a suitable platform for deploying your large language models and diffusion models. Compared to the Inferentia 1, they offer 4x higher throughput and 10x lower latency and support larger models. For image generation on Stable Diffusion, you can achieve up to 80% higher throughput per dollar. And for your large language models, on average, you see 74% lower latency and 4.7x in cost reduction. Each Inferentia accelerator comes equipped with 32 gigabytes of high bandwidth memory, scaling up to 384 gigabytes on the larger instances to enable you deploy your large models with larger batch sizes and to reduce the need to constantly load and unload data from memory. This accelerator will come in 4 configurations. We have the entry-level inf2.x large and the inf2.8x large, each with 1 Inferentia chip for your smaller models. And we have the inf2.24x large with 6 Inferentia chips, and the largest inf2.48x large with 12 Inferentia chips and up to 100 gigabits of network bandwidth for distributed inference. You can fit a 175 billion parameter model on this inf2.48x large, showcasing the power and capability of this instance. The various options for the instance sizes enable you to right-size your compute based on the requirements of your inference workloads. So back to our initial use case, you have fine-tuned the Llama 2 models on your company data to build your chatbot application. And now you want to deploy this model into production for the users to start interacting with it. What performance numbers can you expect when deploying this on Inferentia 2? You can expect up to 4.7x cost to train savings versus comparable EC2 instances on the Inferentia. And if you are optimizing your workload for throughput, you can achieve up to 3.7x higher throughput versus comparable EC2 instances. Throughput is the measure of the number of tokens processed per second by the model, and this is important for larger texts or multiple concurrent requests. For the throughput numbers, for the Llama 2.7b and the Llama 2.13b, we see a 3 to 3.7x speedup versus comparable EC2 instances. And what's interesting is that for the Llama 2.70b, we achieve a reasonable 136 tokens per second, whereas we encounter an out-of-memory error on the comparable EC2 instances. This showcases the capability of these accelerators to handle very large models. You might want to optimize your AI workload for reduced latency, and the latency is the amount of time taken to generate each token. This is critical for your real-time applications, such as chatbots and interactive assistants. For this, on the Llama 2.7b, we were able to reduce the latency by 69% versus comparable EC2 instances from 33 milliseconds to 10.2 milliseconds on the Inferentia. And like we saw for the Llama 270b, we also achieve a reasonable, like the latency of 28.6 milliseconds, whereas we get an out-of-memory error on the comparable EC2 instances. The improvements in cost, throughput, and latency make these accelerators a compelling choice for deploying your models of different sizes to optimize your AI workloads. We have made a significant investment in the global accessibility of these accelerators. This slide illustrates the worldwide availability of Inferentia 1, Inferentia 2, and Trainium across the 23 regions over the major geographical areas of the Americas, Europe, Middle East, and Africa, and Asia-Pacific, China. And because charity begins at home, we'll focus on EMEA, and we have the Inferentia 1 available in 8 regions to deploy your deep learning models, and the Inferentia 2 to deploy your large language models and diffusion models is available in Dublin, Frankfurt, Stockholm, Paris, and London, and Trainium 1 is available in Stockholm. We are working to expand the global coverage to make the accelerators more accessible, and the current extensive reach is important because it enables you to run your AI workloads with low latency and in compliance with local data regulations. It also enables you to deploy your models closer to your end users or data sources, potentially enhancing performance and reducing data transfer costs. So how can you get started to leverage these accelerators? We make it seamless for you to port your AI workloads to these accelerators by supporting integration with a diverse set of tools and frameworks used by machine learning practitioners. To highlight some key partnerships and integrations, we support the popular deep learning frameworks, PyTorch, TensorFlow, and JAX for building and deploying your models. And we leverage OpenXLA for its unified compiler infrastructure and to optimize the model. And we offer our AWS Neuron SDK, which is a robust suite with all the capabilities to train and deploy your models. Python developers can leverage Ray for distributed training and inference at scale. And through our deep partnership with Hugging Face, we have the Optimum Neuron library, which enables developers to leverage the familiar Hugging Face API to fine-tune and deploy the models on these accelerators, as we will see shortly. You can leverage OctoML to optimize your models for these hardware targets, and to visualize and track your machine learning experiments, we support integration with weights and biases. So we also offer the Neuron SDK, which enables you to get all the capabilities of these accelerators. And the Neuron SDK is a robust software suite with all the utilities to support you through your end-to-end machine learning development lifecycle, from model development, benchmarking, optimization, and deployment. It is a robust software stack, so let's break it down. At the foundation level, we have the Neuron Trainium, the AWS Inferentia and Trainium, which are our accelerators, and these are powered by the Neuron devices, which is the compute unit running within the accelerators. The Neuron runtime sits on top of this, and it manages the execution on these Neuron devices. On the right, we have the Neuron kernel interface, and we are very excited about the preview launch of the Neuron kernel interface in a few weeks. This enables you to innovate faster by writing your own custom kernels for these accelerators. This is important in the field of generative AI because the innovation is happening at such a rapid pace. Thus, by writing your own custom layers and operators as kernels, you are able to run this on the accelerators before their official support is available in the SDK. It will support integration with PyTorch and JAX, and we leverage the familiar and intuitive tile-based semantics to make it easier for you to write these kernels. We also offer various tools and utilities for development and debugging, like the neuron profiler, the model checker, and like the profiler and the monitor and the model checker. And we also have the Neuron X distributed tool, which offers all the mechanisms for distributed training and inference that you can leverage. The Optimum Neuron, like the library from Hugging Face, acts as the interface between the transformers tooling and the Neuron SDK to enable you to run your models, datasets, and utilities from Hugging Face on these accelerators. You can run these instances across several Amazon services from Amazon EC2, Amazon ECS, Amazon EKS, Amazon SageMaker, Parallel Cluster, AWS Batch, and Kubernetes. For deploying your models, we offer and support integrations with the popular model servers such as VLLM, Hugging Face TGI, the AWS DJL, TouchServe, and RayServe. We have seen the powerful capabilities of the AWS Trainium and Inferentia accelerators and how they can enable you to optimize your AI workloads for cost and performance, and also seen the robust software stack that you can leverage for the end-to-end development. So how can you get started to fine-tune and deploy your models for your use cases? I'll hand it over to Junior to walk us through the next sections.
Thanks, Troy. I'm super impressed by how cost-efficient and powerful Trainium and Inferentia are. So now I will introduce you a library called Optimum Neuron, which makes it super easy to migrate your training and inference workload to AWS Neuron devices, namely the Trainium and Inferentia. So before we head to Optimum Neuron, I would like to do a small questionnaire to get to know more about the audience. So raise your hand if you have ever used anything from Hugging Face. Awesome, awesome. So, and raise your hand if you have ever experienced or tested with anything on either Trainium or Inferentia, maybe? Okay, it's fewer, but okay. And any of you have ever tested Hugging Face on Trainium or Inferentia? Okay. Well, there's not a lot of you, but that's exactly what I'm here for. So today, before heading to Optimum Neuron, in case you are not yet familiar with Hugging Face, I will start by giving a brief introduction of who we are and what we are working on. So, who is Hugging Face? Hugging Face is an open source community and platform provider of machine learning technologies. We always say that we are on a journey to democratize artificial intelligence through open source and open collaboration. And to achieve this goal, we have the Hugging Face Hub, which is the home of models, of datasets, and demos that we have. Today, on the Hugging Face Hub, we have more than 800,000 of open source models. We have more than 200,000 of public datasets, around 200,000 of Spaces demo. Those are applications that build with either those datasets or models. And with all these resources, as well as the collaborative functionalities provided by Hugging Face Hub is becoming a place where our community members could work, collaborate, and share their knowledge on machine learning. And besides the hub, we also enrich our ecosystem with a bunch of our open source tools. The The idea is that we want to cover and ease the machine learning workflow from data preparation to training, to evaluation, to deployment, to model demonstration, and so on. And here I list some of our open source libraries that are hosted on GitHub. You can see that we have Transformer library, which is probably the most welcome and popular library that we have. You can use Transformer to download, to train, evaluate, and run state-of-the-art model, including those most classic natural language processing model, audio model, vision model, and of course, those most trendy and latest large language model. We also have diffuser library for diffusion model to generate images. We have accelerate library to ease the distributed training and inference on GPUs. And all those libraries I listed here, they are not built just by engineers from Hugging Face. They're actually built through the collaboration and contribution from thousands of community members. Either by opening those issues, raising pull requests to us, writing a lot of interesting blog posts using Hugging Face tools, and so on. Okay, it come back. Using Hugging Face tool. And among those community members, some of them are quite special. These community members are our hardware providers and hardware partners. Today we have, like I just mentioned, that Hugging Face provide open source. You can find open source models, open source public datasets on our hub. But there's the software part, there's also the hardware part, because today those large performance models always come with massive weights that can't be fitted into one single GPU. And we find more and more that the computing power is becoming a scarce resource for almost everyone. And that's exactly why Hugging Face decided to team up with the world's leading AI hardware accelerators to democratize not only from the software perspective, but also on the hardware part. And among those hardware partners, AWS Neuron, namely the Trainium and Inferentia instances, are one of our most important partners. So in our hardware partnership, we collaborate with multiple hardware providers with the Optimum library. And Optimum Neuron, as the name suggests, is a subpackage of Optimum that is dedicated to AWS Neuron device. It's basically the interface between Hugging Face ecosystem and the AWS Neuron accelerator. And the idea of having Optimum Neuron is that we want to integrate seamlessly the Neuron SDK with Hugging Face existing tools like transformers, like diffusers, like accelerate path, and so on. So I saw many of you have already experienced with Hugging Face. If you are already transformer users, diffuser users, accelerate user, I would say you are already experienced user of Optimum Neuron. Because when we decide to design the APIs in Optimum Neuron, we always try to make it as similar as possible to those APIs that we already have in other Hugging Face libraries. And in terms of its support, the coverage, today we support already a wide range of machine learning models, including those most classic NLP models like BERT, Roberta, sentence transformers. We also support vision models, audio models like Web2. We also support, of course, those popular latest large language models like Llama, like Mistral. We support diffusion models by extending the diffusers library. We support like Stable Diffusion XL, and their variants. We also support the adapters for diffusion models like those control nets, LoRa adapter, and so on. And And just like any other Hugging Face library, Optimum Neuron also comes with a very detailed documentation, including documentation for the APIs, end-to-end examples, and tutorials. And if you are a SageMaker user, we also have tutorial dedicated to using Optimum Neuron via SageMaker. So now you might have a rough idea about what is Optimum Neuron, but how does it look like? So today I will walk you through a very classic example, probably the most classic one. We will build a chatbot together by using Optimum Neuron on Trainium and Inferentia. We will start by fine-tuning a foundation model with our own dataset on Trainium, and then we will use the fine-tune checkpoint and deploy it on Inferentia to build a chatbot. Today here, as you see, I picked something quite special. I picked Llama 370B as example, because Llama 370B is a very performant large language model. And it's performant, but it's also very big, which means that it can't be fit into one single neuron device, which needs us to apply those distributed training features that we have implemented in our Optimum Neuron library. As you can see in the code snippet here, maybe it's not that clear, but I will explain it all, so no worry. Here we use an API called Neuron Trainer. For those who have already used Transformer, do you have any idea about the Trainer API? If you have, please raise your hand. OK, awesome. So basically, the Neuron Trainer is the neuron version of Trainer in our Transformer library. The Trainer API is a class that fully manages the training and evaluation loop. And just to mention, except for Neuron Trainer, we have another API for the training in Optimum Neuron, which is called Neuron Accelerator. So I think so many of you have maybe tried with the Accelerate library of Hugging Face. So if you prefer more customizable training loop, you can also use the Neuron Accelerator, which is the equivalent of Accelerator in our Accelerate library. Yeah, let's go back to the training script. So with using Neuron Trainer, we need to compile multiple distributed training techniques, which includes the tensor parallelism, the pipeline parallelism, and the zero redundancy optimizer on stage 1, which just shard the optimizer states across multiple devices. And for Llama 370B, since it's a very large model, we will need to create a cluster with at least 4 Trainium nodes, which needs us to apply multiple node training. So for now, I think I have talked about a lot of distributed training features. It might sound a little bit complex and perhaps a little bit intimidating. But no worry, because actually the goal of Hugging Face Optimum Neuron is to manage all of those complex distributing loops for you through a Neuron Trainer. Let's break it down. Let's break down those distributed features, feature by feature, to see how we can enable it. So we will start with tensor parallelism. So what is tensor parallelism? It just shards the model's matrix multiplication across multiple devices. So it can reduce significantly the parameter held by each worker, which allows us to scale up and train larger models. To set this feature up, what we need to do with Neuron Trainer is just to configure one argument, which is called the tensor parallel size here. So by setting up the tensor parallel size, which is the number of workers that we want to shard our matrix multiplication, we can enable this feature. And we have a second type of parallelism, which is pipeline parallelism. It basically shards the model's layers and blocks. It dispatches the model's layer and block to different devices, unlike the tensor parallelism, which actually is an intra-layer parallelism. And to enable pipeline parallelism is also just like tensor parallelism. You just need to set up one argument, which is called pipeline parallel size. And now let's go back to the training script. We have talked about 2 types of parallelism. To enable all of this and launch our training, first of all, we will need to load the model. Here, something different is that we use a context manager called lazy load for parallels. We need to set up those 2 arguments that we talk about to lay the model lazily so that we can avoid go out of memory. Once we instantiate the model, we will need to configure the distributed training features through the Neuron Training Arguments API, which is similar to the training arguments of transformers. We will need to set up the tensor parallel size we just mentioned, the pipeline parallel size we mentioned, and to enable the zero redundancy optimizer stage 1, we just need to set 0, 1 equal true. Easy, huh? And with the training argument, we will instantiate a trainer, the neuron trainer by the model, by the data sets, and the training argument we just configured. And now we are ready for launch our training script. Here is an example of command lines in which we launch the training script with torch run either on one single node or on multiple nodes. Just to mention that after the training, since we do distributed training, we also need to consolidate the sharded checkpoint so that it can be run in different distributed configuration during the inference. So now we have already fine-tuned our large language model. Now let's try to deploy it with Inferentia and build our own chatbot. Today we will use another API in Optimum Neuron, which is called Neuron Model for Causal LM. I think for those transformer users, you might be familiar with it because it looks just like the auto model that we have in transformer library. And the idea is also very similar. It's just for the first step, it's a little bit different, is that we need to compile the model first. So we need to set up the compiler arguments in which we need to decide on how many neuron cores that we want to deploy the model, and we need to set up the precision. I want to mention that for the compilation, although it's a step unavoidable, actually the Optimum Neuron team made quite some effort to make it more intuitive, faster, and more flexible, in which, first of all, you can use the single liner here to compile the model by sending all the information in it. You can also use our Optimum Clear to compile the model as well. And beside all of that, we also set up a caching mechanism in which we will cache the compile artifacts either locally or remotely unless you disable the caching, so that after the first compilation, if you want to compile exactly the same model architecture a second time, it will fetch directly from your local the pre-compile artifact. So it will save you some recompilation time. And we also set up a public repository in which we have already pre-compiled and cached a lot of popular large language model and stable diffusion model. So if you want to test with some of it, you can enable the caching and it will fetch directly from our Hugging Face hub, which will save you some compilation time. Yeah. This is for the compilation, which could be a little bit tricky. And now we go back to our routine. Once we have the compile artifact, we can load the artifact with the neuron model for Causal LM API, just like the auto model for Causal LM API. And we can send a prompt, we can instantiate the model, send a prompt to the model, and boom, we are ready to generate the answer with the chatbot we just built on Inferentia. And here's the answer of the chatbot that we built with Optimum Neuron by using Trainium and Inferentia. So I just walked you through some code snippet. It might look a little bit messy. I don't know how you feel, but if you are a SageMaker user, actually there is also an easier way, which is you can go directly to the model page of Hugging Face Hub, to the checkpoint that you are interested in, you can click the deploy button on the model card, and it will jump out this window. You can choose one section named AWS Trainium and Inferentia. Here you can see a template for which you can copy-paste it and launch your inference endpoint directly with the corresponding checkpoint on SageMaker. And yeah, that's it. That's all I want to present for Optimum Neuron. So if you feel interested or you want to know more, feel free to try out our example on our Hugging Face Hub. And if you have any question, feel free to ping me and the team on our GitHub repository as well. Now let me hand over to Roy.
Yeah. As we conclude, we've covered a lot of ground today. We've seen how the future of AI is not in bigger models, but smaller and more efficient models that are fine-tuned for your use cases. We've also seen how the AWS Trainium and Inferentia accelerators can enable you to optimize the AI workloads for both cost efficiency and performance in the cloud. And the Optimum Neuron library will streamline the end-to-end fine-tuning and deployment workflow. These tools and instances empower you to innovate faster, to disrupt the industry, and drive real business value. We are excited to see the amazing solutions that you will build on top of this. And thank you very much for your time and attention. We hope you enjoyed the rest of the summit. Please take a moment to fill in the session survey. Thank you.